Okay, so yesterday, by the end of the lecture, I was talking about these tap equations that give access to these sets of m's that fix the set of m's that are extremes of a certain free energy function that of the m's, which plays the role of the Ginzburg-Landau free energy for more simple problems. And it turns out that these equations have many solutions, which are extremes of the free energy density, and that in a pictorial way, one represents with this sort of complex landscapes, where you have a lot of minima, a lot of maxima, a lot of saddles. And of course, as I said also by the end of the talk, this is a little bit misleading to draw these pictures like this, because these substrates is large dimensional itself. So, geometry in large dimensional spaces is not so intuitive to think about. So this was also this is the definition of how you fix these extremes of the free energy landscape, and then you can look at the stability of those by looking at the Hessian at the extremes. Now, features are that, okay, you have n local order parameters to deal with. The saddle points are heterogeneous in the sense that the MIs differ from site to site. At high temperatures, there is only one trivial solution, which is all the MIs equal to 0, which is like the paramagnet or the disorder configuration. But at lower temperatures, you start seeing appearing these different solutions that you can label with an index alpha. And the way in which they appear and the way in which they are organized in height in this free energy density landscape is highly non-trivial, but can be studied. There are methods in physics that allow you to study all these and count them and see how many there are at each level of the free energy density, and how many there are of each kind of stability at each level of the free energy density, and so on and so forth. Of course, there is the trivial symmetry of up and down, so there is a doubling of solutions, but this is a little bit trivial. But then there is also this non-trivial degeneracy that you see appearing by solving these equations. So, as I said, the tap free energy density can take different values at different sets of these solutions, which is just like saying that you have, tops of these mountains at different heights, and depth of the valleys at different heights as well, and so on and so forth. So you have a full range of free energy densities over which you have all these solutions, and then you can try to characterize them statistically in some way by counting them, and so on and so forth. So it's like the Himalayas or the Andes or the Alpes with this very highly complex structure, but again, two-dimensional, but it's large dimensional itself. Okay, this I can jump over that. I said that you can count them. Okay, there are ways to do these calculations. Basically, what you have to do is you have to integrate over all the possible MIs, asking that MI is equal to one of these solutions. And there are tricks to do that. And like this, you can compute what are called the complexities. So the complexities is like an entropy. It's a logarithm of the number of solutions of the tap equations constrained in the way that you like to do that. So, for example, constrained to have a certain free energy density. So then it's like making a cut in this landscape and looking at how many extremes of the landscape belong to this cut with some little width around the level that you have chosen. Or you can even, constrain to have a given degree of stability, a number of positive and negative eigenvalues of the Hessian matrix. So all these things have been done, and depending on the particular disorder model you work with, not on the typical interactions you're working with, but for example, distinguishing between having two-body interactions with random couplings between them, or three-body interactions with random couplings between them, you will have different generic forms of these landscapes. And these, again, are like ways of characterizing universality classes in these disorder systems, and classes which are linked to realistic realizations of glasses, so classes of glasses that appear in nature. So, for example, with two-body potentials like the Sherrington-Kilpatrick model I was introducing, you capture features of spin glass samples, like instead with three-body interactions in the models, so like doing Si, Sj, Sk, and putting a coupling strength with three indices, coupling these three spins, you capture features of fragile glasses, ones with no quench disorder, but that somehow self-generate their disorder to make these models have an impact in their description. So, okay, this one I can jump. All these I will jump because it's a little bit specific. I have it from other lectures. I'm not going to touch upon the replicas and other special methods to deal with these problems. So now let me go to dynamics, because the main subjects of my lectures has to do with dynamics. So what happens with experimental samples? So are they able to reach equilibrium or are they not? And if they not, how do they behave? So the answer is that they're not able to reach equilibrium in experimentally observable times if you pick a spin glass and you let it evolve after a quench. So these curves here are have been obtained in Saclay, in one of the labs in Paris. And this group was working with, well, different kinds of spin glasses. This is an insulating spin glasses. It doesn't matter what it is. It's some spin glass sample. And what they have done is they have done the same kind of experiments that I was discussing in the context of the analysis of coarsening problems. And they have measured correlations and linear response functions in these magnetic samples. So concerning the correlations, what they do is that they trace the evolution of the magnetization of these problems. These problems are not magnetized, so this is just magnetic noise. So it's something that fluctuates about zero. And they correlate this magnetic noise at different times after the quench. So like what I was measuring correlation functions in time, in two times, for the just easing model that I discussed a couple of lectures ago. So what you do is you let time evolve at different waiting times, which I'm calling T prime here, because in the plots they are called T prime. At different T primes ordered in this way, you get these different curves ordered, from bottom to top, following the colors in this time axis here. And what you see is that, like in the coarsening problems, you have a regime of short time differences where all these curves fall on top of each other. And then there is a regime of long time differences where they deviate and they express these agent properties of the sample. So it's very similar to what was observed in the coarsening phenomena. You have here the development of the plateau. Of course, it's hard to say whether it's a strict plateau with a finite value of the correlation at which the curves will sort of stop before going down again, or this is a little bit inclined and it's more like in the critical relaxation of the coarsening systems. This is, with experiments, it's always a little bit hard to be sure of what's going on. But okay, this is what is going on. And these experiments had been made in the group of Miguel Ocio. It's a very difficult experiment because it's a tiny signal that they had to correlate and get, average over them. So it was really very, very difficult. Simpler to make experiments are the ones of the linear response, because there you perturb the sample with some field and then you let it evolve afterwards. So what they have done here is that they applied a field from 0 to T prime, and then they switch it off, and then they see how the magnetization, which now it's high, decreases in time after switching off the field. So this is what they're called thermoremanent magnetization experiments, and or field-cooled magnetization experiments. And what they do is they look, as I said, the relaxation of the magnetization after periods of applying this field, which are longer and longer for the curves, or again, ordered from bottom to top. So you see again the waiting time dependence here, expressing the aging phenomena. You see again that there is a part of short time dependencies where actually there is no waiting time dependence. All the curves go together, and then the waiting time appears. Again, whether there is a plateau developing or not, well, it's not that clear. This is the best that can be done. I mean, longer waiting times in the experiments are impossible to reach, and this is in seconds. Okay, this is the kind of 1 day length experiment that can be done.
Leticia, so what are the typical waiting times in this, let's say, the first plot?
Well, I didn't write them, but again, it's of the order of minutes. Yeah, because I think that the best they could do is of the order of a day in the measurement, because they have to keep the samples cold, and there is problems of keeping the temperature fixed, and so on and so forth. So it's it's of the order of minutes as well. So longer time difference is 1,000, and I think that the longest waiting time here was also of the order of 1,000.
Okay. And this the magnetizations are like local magnetizations, I guess, right?
No, they're global. They're global. So
sample. Oh, okay.
It's a full sample.
Okay.
These are small samples, and these magnetizations fluctuate a lot. So this is I don't know how many averages they had to do. You see, these curves are not as nice as these ones. So,
okay.
So it was experiments of. It was a thesis of Didier Hérisson, so it took like 3 years for these experiments to be done, and Miguel was preparing the experiment beforehand, so it was a really huge effort. So what are the glassy microscopic mechanisms behind these? We don't know. I mean, because locally there has been very little experiments done, and there's no local way to have a handle and see whether there is some local order developing that one cannot for the moment identify or not. So this is what has been done. Now, if you compare these figures to these ones here, which on the left I had the 2D easing model with no disorder, just the normal one, which is doing ferromagnetic coarsening at low temperatures. And on the right, I have something very different, which is a Lennard-Jones sample of particles in interaction at low temperatures, relatively high densities, but no quench randomness either. So you see that, okay, quantitatively, there is maybe some difference in the form of the decays at the long waiting times, but qualitatively, the pictures are very similar. So this is just a spin-spin correlation function. This is density-density correlation functions in the particle systems. So you have similarity between these correlations and these correlations, but okay, in this case, you know what's going on. There is this, coarsening of ferromagnetic locally ordered regions. In this case, you don't see either any kind of local order developing, but you have these arguments about caging that can be used to explain the fact that you have, the approach to a plateau here, and then the structural relaxation that makes the curves deviate and relax further from the plateau and have the waiting time dependence appearing. So, okay, so there is similarity in the decay of the correlations in systems which are very, very different, ones with coarsening, ones which are glassy but no quench randomness, and the other ones which have quench randomness. What can we do with theory? With theory, what we can do is treat exactly the evolution of problems which are either spin models on fully connected graphs with quench randomness, or also problems of particles in interaction moving in infinite dimensional spaces. So you take the dimension of space d to go to infinity, and then there are simplifications, of course, that arise, and then you can also write the kind of equations that I will show you later on that couple correlation and linear response function, and just then becomes a problem of analysis, how you solve these integral differential equations that look very complicated, but have either numerical solutions or even analytic solutions in the long time limits. So this is things that can be done exactly at the level of solving models. Of course, the models with which you work are not exact models for the experimental samples, because either you put them on a complete graph for the spin problems, or you take the limit of infinite dimensions for the particle systems. Otherwise, you can work with the exact models for the experimental samples and do some approximations on them. And these are the kind of approximations which are like self-consistent resummation of graphs in some perturbation theory that you can set up, or they also go under the name of mode coupling theory in the context of glassy systems. There are different ways of naming these approximations, but the procedure is slightly different. So you start from an exact model, let's say, and then you make approximations on it. And it turns out that in the end, many of these approximations give you the exact equations that you find for the approximate models. So there is some kind of, in the end, you're doing the same. No? You're doing some approximation for the exact or some exact treatment of the approximate, and you end up with the same kind of equations that then you solve. And these equations capture at least the qualitative features of the glasses, the ferromagnets, or the spin glass problems. Of course, there are some properties that distinguish these three that I will discuss later on, and that have to do with the behavior of the comparison between the linear responses and the correlations that how the fluctuation dissipation theorems between them are violated. And the way in which these are violated allow you to distinguish ferromagnetically growing systems or coarsening systems, glasses without quench disorder, and spin glasses. So to go, how do you derive these equations? Well, you derive them from writing down Martin-Cicharot's, for example, it's one way, Martin-Cicharot's generating functionals and just making some manipulations of them by introducing auxiliary functions which turn out to be the correlations and the linear response themselves. And because of the completely connectedness character of the graphs on which, or the larger d dimensions, you can make saddle points on these generating functionals and go ahead, and then in the end you derive these Schwinger-Dyson-like equations that couple correlations and linear responses through integration over time derivatives which come from the Langevin dynamics, some kernels here that in general you don't know, but for these particular models you can compute. And these self-energy and vertex are functions of the C and the R themselves. So C is the correlation function, R is the linear response, sigma and D are these kernels. And okay, the form depends on the choice of the model or approximation you are using. And for example, for these p-spin models, which I'm going to write on the blackboard, and that put together the cases of coarsening, spin glasses, and glassy systems, for them, the Hamiltonian looks like this. So these are taken from PDF. They are Quench random variables. And so P is a parameter. If P is equal to 2, you have two-body interactions. If P is larger than 2, you have many-body interactions. And then you have to normalize the PDF of the JIJs, as I mentioned yesterday, to make this thing have a nice larger limit. And here you see you're summing over all possible ways of linking these P spins that appear in the each of the terms in the Hamiltonian. And now what happens is that if you take P equals 2 and Ising spins, you are with the Sherrington-Kilpatrick model, which is a good model for spin glasses. If you take spherical And to body interactions, you have the spherical SK model, this called this way, or P equals 2 model. And this is a good model for coarsening systems. And if you take P larger than 2, this is a good model for what I call fragile glasses. So glasses with no disorder. And then you can make mixtures of these P's, and you can also get what people call strong glasses in the context of glasses systems with no quench disorder. So, with this model, Hamiltonian, by playing with the choice of this parameter P, you can sort of cover all the possibilities of these out of equilibrium systems with glassy properties, or with out of equilibrium no glassy, like in the case of the coarsening ferromagnetic systems that I discussed in the second lecture. So this is why we like so much this set of models, because they are so, they are very universal in the scope of what they can do. And on the other hand, you can distinguish them in sets of groups of models and then capture different kinds of phenomenologies.
So is by spherical model, you mean the O3 one, or with the spherical constraint?
I mean with the spherical constraint. So I mean, by spherical, I mean
sum over, equal to n. I see.
This one. And actually, when I said the case of the fragile here, you can do it either with the spins which are easing or spherical, and both of them give you this fragile glass sort of.
But in general, there are these ON generalization as well of these models.
There are, yes, you can do some kind of ON generalizations as well. But okay, we'd like to work with these ones. Yeah. Okay. Actually, the ON model, the usual one with the lambda 5/4 potential, is very similar to this spherical coarsening system. It's a little bit richer because you have the space dependence as well in the field. So you have a bit more information than with this one. But okay, there are many features which are very, very similar.
But spherical model is exactly solvable, right? Without disorder. So with disorder, you could also solve it?
Yes, you can also solve it exactly. And you can do lots of things. You can, of course, write these Schwinger-Dyson equations, but of course, but it's a little bit more difficult to solve it like this than to solve it directly in the basis of actually eigenvectors of the interaction matrix. So you can solve it, directly. It was proposed by Kosterlitz, Thoules, and Jones in the 70s as a very simple model with disorder, and then many people, including myself, looked at it in different ways. Yes.
Okay, thanks.
Yeah.
Hi.
Yes, hi.
Some quick question. So
Yes.
you mentioned that this for p-spin models, you get this sometimes exactly Schwinger-Dyson equations.
Yes.
So I was wondering, like in the context of Sachdeva-Kitev models, like you encounter similar set of equations on the Keldysh contours.
Yes.
Sometimes these equations turn out to have some time reparametrization variant solutions.
Absolutely. Yeah.
Does they have any significance in this context?
Yes, of course. Yeah, we have them, and we also realized this in the past. And I said that these equations can be solved analytically. So let me go here. So you see, this is a sketch of the solution of the equations. So as in the experiments and so on that I showed you, there are two time difference regimes in these equations. So there is one approach to the plateau. So the plateau here is a true plateau. You can prove it. So there is a first stationary relaxation towards the plateau, which is rapid. And then there is a second relaxation below the plateau, where in this, you see, this is a logarithmic scale in my sketch. The relaxation is much slower. Now, how do we solve these equations? We solve them by proposing that the full correlation and the full linear response separate in an additive way, with a first term which is representing the approach to the plateau, and a second term which is representing the decay from the plateau. Now, if you plug in this assumption into these equations, you write the equations in the regime of time differences, which is short. You write the equations in the regime of time differences, which are long. You assume that the separation is sharp with a plateau here. And then what will happen is that when you look at the equations in the regime of large time separations, then you can drop the time derivatives here, because they are, you show that they are smaller in waiting time dependence than all the other terms in the equations. And when you do that, you have this time reparametrization invariance that also appears in the Kitaev-Sachdeva model. And we thought about it, very in the past, in the when we were solving these equations. And if you're interested about the way in which we deal with this time reparametrization and the things that it implies, which I will not be able to discuss here, I would suggest you to have a look at this review article that we wrote with Claudio Chamon. And myself. It must have been 2007, roughly. It's in JStatMech, the journal of CISA, and then, okay, we talk a lot about how this time reparametrization is related to heterogeneities in space, in the behavior of glassy systems, and so on. So yeah, it's something that also appears in our problems. Yeah.
So one more follow-up actually.
Yeah.
On this Goldstone manifold, like this derivative term can be important, and it lifts the degeneracy in that manifold, right? So
yeah.
This kind of aspects did people speak about in
no.
context?
Okay. This kind of aspect we were not able to solve in these equations. These equations are a bit more complicated than the ones for the Sachdeva model, because the Sachdeva doesn't really have a glassy phase, right? It's always like paramagnetic. While we are interested in this glassy phase, and okay, we have this issue of having to deal with correlations and linear response, and so this problem of fixing the parametrization with the putting back the effect of the time derivative and doing the matching. In our terms, we were calling it the matching problem. So matching how this thing decays here with how this thing goes away from the plateau there. It's open in our milieu.
Okay, so this C have some replica indices also, is it?
No, because out of equilibrium, starting from random initial conditions, you don't need to use replicas. You have to use replicas only if you want to start from an initial condition which knows about the Quench randomness, which could be is an interesting question as well. No, you can say, okay, I start from initial conditions which are determined by the Quench randomness in some way, and then I let them evolve. However, here we are not doing that. We are saying we start from an initial condition which is completely disordered, there's nothing about the JIJs. Then we quench it, low temperatures, and then we see what happens.
Yeah. Thank you very much.
You're welcome. Yeah, actually, the time reparametrization invariance, you see, it was written here in the slide. I wrote it, but yeah. So, okay, so in this context, we see by solving these equations that numerically, that the kind of parametrization which is chosen by the dynamics is like a power law. But we don't have an explanation of this power law, like, we don't have an interpretation of this power law in these models, like we did have in the case of the coarsening system when I was talking about this Allen-Kahn argument and so on and so forth. So, okay, this is something that it's like that. Now, what about these fluctuation dissipation relations that allow us to distinguish these three sets of out of equilibrium dynamics here? So the correlation functions decay in this way, sketching this this picture here. And if I look at the integrated linear response, it will do sort of the opposite, in the sense that it will grow towards a plateau and then detach from the plateau in a waiting time manner. Actually, these plots are taken from the review with Claudio that I'm citing here. And then in equilibrium, you know that these two quantities are not independent. They are related by the fluctuation dissipation theorem, that basically what it says is that if you make a parametric plot where you plot chi against c for a given waiting time as a function of, by using as a parameter to make the construction, the t minus the waiting time, you should get a straight line with a black just slope, the black straight line, which is given by -1 over the temperature of the bath, or the temperature in which the system is in equilibrium. So there shouldn't be any waiting time dependence to start with. So for all waiting times, you should see the same straight line. And this straight line is just a property of equilibrium. It's not a property of the particular model you're looking at. If you look at, any of these models, if they are in equilibrium, they should construct this straight line in this way. Now, what is observed is that they don't build a straight line. What they do is that they build this straight line for short time differences, but at a value of the correlation, which is the one of the plateau here, and at a value of the chi, which is at the level of the plateau there, the straight line of the equilibrium behavior is broken, is lost. The curve leaves it, and then it does something else. So what the something else does depends on the kind of model you're working with. So here I just plotted the case. You can do it on the blackboard. Well, I will do it. What can I do it? I will do it here with the blackboard. So this is, well, the C of Claudio, and then the linear response here. This is the piece where the correlation goes from 1 to the Q of the plateau. This is the chi of the plateau, chi plateau, let me call it. And then what should have followed like this deviates. And there are three possibilities. So it's either going like that, like this, or making a curve. And this flat thing is the case of coarsening. This straight line is the case of p larger than 2. And this curve thing is the case of p equals to 2 with descending spins. So it's the Sherrington-Kirkpatrick model. And if you want to put it in terms of systems, so this is the spin glass. This is the fragile glasses. And this is, okay, coarsening, for the ferromagnetic coarsening I was talking about. So in the terms of model, this is the P equals to spherical model. Let's not put coarsening in red because I was putting the. So you have a way to distinguish these, systems and models by looking at how the FDT is modified below this plateau here. And what you see is that, okay, for the coarsening, I was telling you in my lecture on coarsening that the coarsening systems have no response, basically, in the regime where the interfaces are moving. So the interfaces don't respond to, so this is why this curve becomes flat here. For the structural glasses, you have a rather simple violation of FDT given by a different slope, which is not given by the 1 minus t of the equilibrium, but is given by another slope. And then for the scale, you have a curve thing. I don't have time to discuss this. I chose not to do it, but let me just tell you that what's going on here can be interpreted in terms of an effective temperature that is controlling the behavior of the large-scale relaxation in the problem. And that, okay, this effective temperature is particularly simple in the case of the fragile glasses because it just takes one value. It's simple, but a bit more weird in the case of coarsening because it goes to infinity, and this is why this thing is flat. And it's rather complex in the case of the Sherrington-Kirkpatrick model because since it's curved, you see the effective temperature I'm identifying from the slope of this curve. So there is a continuity of effective temperatures here. And indeed, this is related to the fact that in the Sherrington-Kirkpatrick model, there is a continuity of timescales in the evolution below the plateau in this problem. So it's like if there were a continuity of these time parameterization functions that are chosen by the dynamics, one after the other one. Okay, this has to do with ultrametricity. It's you know, a lot of technical issues would arise to discuss this. But I just wanted to mention it to give you some background of what's behind this. Okay. So, okay, I'm going to summarize what I wanted to tell you about disorder systems, and make some let's you know, some discussion after this part. So what did I say? So first thing I said is that in equilibrium phases, so in equilibrium at low temperature in these problems, there's a large number of metastable states, even equilibrium states, that scale within the number of degrees of freedom in the problem, and possibly it's a number which is exponential in n. This will depend on the model, will depend on the level of the free energy density at which you look at. But you know, in certain regimes, you have even an exponentially large number in n of metastable states in the problem. So the complexity is proportional to n because you take a log. So it's like a, you know, macroscopic entropy of states which is appearing in these systems. There is a non-trivial organization of these states, which is linked to the name of ultrametricity in certain, again, in certain cases. Okay, I didn't discuss so much so this, but it can be studied and analyzed in detail. There are phase transitions of a new kind which appear. I didn't talk about this either, but in the case of the P larger than 2, many bad interacting cases, there is what is called the random first order phase transitions, that it's a name that appears attached to the description of fragile glasses. And okay, this is something that appears very much in the literature, has been discussed in a lot of details. Now, experimentally, what happens, these systems remain out of equilibrium at low temperatures because the equilibration time goes beyond the observational time, and there are aging effects. We don't have a very good understanding of, you know, in local space, in real space, what these aging effects are due to. So we don't have a way to identify local order developing as we do in coarsening systems. Then there are these violations of FBT with the appearance of effective temperatures that, that allow us to distinguish these three kind of samples, allow us to, you know, if you have an effective temperature definition, you have to check whether it complies with properties of thermodynamics. I can tell you that it does. So it can let you think about extensions of thermodynamics out of equilibrium. So again, the literature is huge around these ideas. I will not discuss them here, but just let them know to you. And in disorder systems of spin glass kind, you have weird effects in the way the system reacts to changes in the temperature of the bath. This is sometimes called temperature chaos. It also has a lot of implications in experiments. And I just wanted to mention them here because yesterday, before the beginning of the talk, I was asked by Abhishek which were the differences between problems with quench randomness and problems with you know, frustration, fully frustrated models as the antiferromagnet on a triangular lattice. And I started to reply, then the connection to the Wi-Fi went off. I didn't reply very well, and then the lecture started. So I said, okay, let me add now here a transparency to answer at least partially that question. So which properties of frustrated magnets, which I didn't discuss in my lectures, but okay, which are some properties of frustrated magnets which are absent in spin glasses and even in glassy systems. So I could think of these ones. So for example, in frustrated magnets, you often have disorder by disorder phenomenon, which simply consists in the fact that at zero temperature, you have a ground state which is highly degenerate, with many configurations which are, you know, of equal energy and equally probable, like in the antiferromagnet on the triangular lattice, the configuration in which there is one link which is frustrated in each triangular plaquette. So in this kind of frustrated magnets, this is quite often the case, that you have this entropy of the ground state, which is macroscopic. But this entropy is lifted, this degeneracy, sorry, is lifted by just an epsilonic temperature fluctuation, which is choosing one of these equivalent ground states, because if its own degeneracy is larger, so the entropy contribution that you get over this ground state at epsilon temperature, when you construct the free energy and not the energy, then is making the free energy of this particular state lower than the one of the other ones. And these particular states is often ordered. So this order by disorder phenomenon proposed and analyzed by Villain in the 70s, I think, 80s. There's nothing like this in problems with quench randomness, as far as I know. So this is one particular feature of frustrated magnets, which is not present here. Then often in frustrated magnets, you can identify a local pattern that repeats. So for example, in the triangular antiferromagnet, you have one link in each plaquette, which is broken. So, okay, again, there's nothing like this that you can easily identify in problems with quench randomness. Then there are, okay, frustrated magnets like spin ice, for example, spin ice in 2 dimensions, or the model as vertex models, for example. They often have other phases as well as the disorder ones. In these other phases, you have usual coarsening phenomena and so on. Again, the other phases are not necessarily present in the spin glass problems. And then the disorder phases in these frustrated magnets are often critical. Okay, again, then we don't have critical phases in the spin glasses. So, and these temperature chaos and weird regeneration and aging effects that we obtain under temperature cycling protocols, as far as I know, they have not been seen in frustrated magnets. So, okay, these are some differences that I could quote here between problems with quench randomness and problems with frustration, just frustration. Okay, so this is what I wanted to say about disorder systems. So maybe I could go to the chat and see the questions there. What is the difference between quench randomness and quench disorder? No, I'm using the words in the equivalent ways. So yeah, quench randomness and quench disorder is the same. How does the temperature affect the dynamics of quench disorder models, say random field Ising models? Okay, so random field Ising models, let me erase here. So the random field Ising model in 3 dimensions has a phase diagram, which looks like that. So this is the usual temperature over J axis, and this is the strength of the variance of the random fields over J to make it adimensional. And then there is some kind of phase transitions like this. So this is the usual one with no random fields of the Ising model. And then you have a disorder progressively killing the other phase. This is a ferromagnetic phase, and this is a paramagnetic phase. So if you do quenches as the ones I was doing from infinite temperature, somewhere here, to within the ferromagnetic phase, what you will see is coarsening of the ferromagnetic phase. So you will be able to identify a growing length, R of time, and the parameters, the control parameters, like this. And the form of this R was also studied by Villain, who did lots of things, Jacques Villain. And he, well, first of all, argued that this should go like a log of t over some time scale, possibly with some exponent here, and with a prefactor here, which depends on the parameters. And he has, predictions for how this prefactor depends on these two parameters, T over J and H over J. So the temperature dependence and the parameter dependence is here, it's in the prefactor, it's not within the time dependence, actual time dependence of the growing length, nor in the exponent. So, okay, so this is just, they do normal coarsening, but with an R, which is much slower than in the coarsening without Quench randomness. And the reason is that the fields are pinning the interfaces, and then sort of stopping the growth of the ferromagnetic order differently in different places. And yeah, and this is slowing down the dynamics and making the R slower than just power law. Of course, this form, you have to be careful when you really work on this line here, where there are, well, okay, then you have to distinguish. This is just the pure problem with no Quench randomness. So the form I'm giving there is, for H different from 0. Then temperature, as I said, what it's doing is, temperature is if you have a pinning of an interface, so you have your system, I'm drawing it in 2D, but you have interfaces between different regions of ferromagnetic order, and if you have the fields, then okay, these fields are going to pin the interfaces, not let it move so much, that it will make the interfaces rougher. And with respect to the ones of the problem without disorder, temperature is going to try to make them move these interfaces because it's agitating the system, so it's trying to make it move. So there is this competition between temperature and fields that it's going to eventually make the interfaces move, but it will take time to do it.
Any example for annealed disorder?
For annealed disorder, no, I don't have examples, but yeah, probably should look at that. But in usual, I mean, most of the people interested in Quench randomness, they work with a Quench disorder because it's there that the more difficulties arise. But I mean, yeah, there should be. I mean, I don't have now examples in mind. What the thing that has attracted a lot of attention coming from the the cosmological community first, and then the quantum community, is instead of doing instantaneous quenches, to do quenches which have some time dependence in the way in which you tune the control parameters, and see how this modifies the scaling of the form of the R and these sort of things. But for changing the control the JIJs simultaneously, I don't have examples to show here. Yeah.
So, like in general, annealed disorder would mean JIJs are changing slowly with time, but
Yes.
they are also random. It's some kind of process. Some process is changing it. Markov process. I don't know.
Yeah. You could write another Langevin equation, for example, for the evolution of the JIJs, and play with the time scale of the way in which this evolution occurs. So, for example, I don't know, with the correlation of the noise or different ways to do it, and see the competition between the two. Yeah.
Okay.
Yeah.
No, it should be okay.
Yeah, in the context of this time reparameterization, I was wondering, like typically in many glassy dynamics, in the slow relaxation process, people try to fit with stressed exponentials. But if we have some time reparameterization for these Dyson equations, we sort of expect some power law like behaviors in time, right? How to like sort of put them together?
No, because you can have any. The thing is that once you've dropped the time derivative in these equations to deal with the behavior, actually what you can show rather easily is that the correlation function in that regime, so in the aging below Q, will be a function of h of t over h of t weighting. This is what you can show. You see that this has exactly the same form of the scaling hypothesis I was using for the for the coordinating system.
Yeah.
Only
Yeah.
that here I don't have an interpretation for the age. And so for all h of t, the equations are solved. So this is the time reparameterization invariance. What the equations, the remaining equations fix is the form of the f. But they don't fix the h of t, because in the equations you can change t by h of t and they remain untouched. So you can have any h of t to solve those equations. Then when you do the numerics and you solve the equations exactly, because they're causal, so you can construct the solution of the equations for the PIN problems show you that if you scale, we know here I call it R, if you scale with an R that goes like a power law, then the curves go onto a master curve. So this H, the true H, seems to be, for these models, a power law. But okay, I mean, we don't know how to solve, how to do this fixing of the H of t with these equations.
Oh, so that means like there are multiple solutions which are available, which are
Exactly.
invariant, but picking up is a challenge from physicists.
Exactly, exactly. So in the context of dynamical systems, this problem was called the shooting problem, I think, or yeah, I think it was called the shooting problem. So for simpler for simple differential equations, what happens is, which is the same as for us, but we have two times, but they had only one. Often what you have is that, okay, you have some differential equation, you can solve it for t short, okay, you have your x of t for t short. And then for t long, you cannot solve it exactly, but you make some approximation that gives you many solutions. So x1 of t, xn of t, let's say, even a continuous, some set of solutions parameterized by some continuous parameter. But you know that this equation, if it's causal and there's nothing special, no bifurcation in the middle, nothing wrong going on, this equation should match, I don't know, the x5 of t here in time. So this one should match this one. But it's very difficult to do it analytically, which is the one analytically that you really go and match in the long time limit. So for us, it's the same thing. So we know the exact solution at short time differences because we know the form of this one. We do some approximation in the equations to obtain information about how they behave at long time distances. But this set of solutions is parameterized by this H, and we don't know how to fix the H. So this is the way.
So this derivative term like sort of picks up roughly in a sense, right?
It picks one of them, yes. It's in the end, it will pick one of them, is the one that fixes one of them. But
so the solution with cheapest cost of the action, like can that be identified as a actual one?
Yes. Yeah, that should be. Yeah, actually, what we did with Claudio in the 2000s was to not derive, because it was, I mean, we didn't know how to do it, but argue which was the form that the action had to take, an action for the H, and then, okay, in this way, argue which were the H's that should be picked. But yeah.
Okay,
But
thank
it was
you.
an argument. It was an argument. It was like writing a sigma model, if you wish, for the H, basically. Yeah.
Okay, I'll check out your review.
Yeah.
Thank you.
Okay, thank you. You're welcome. There are other questions on this part? Okay, so if there are no other questions on the disorder systems, maybe I can switch and tell you some words, tell you something about the first of all, I have to stop sharing, and then I kill this one, and I will open the one on the active matter. Let's see how much I can tell you. Not much, but I will try to tell you something about active So now I have to do the share screen. Let's see if this was the one. Yes. So this is the one. So I will enter full screen. Okay, so let me mention, because I want to tell you the kind of things that we have been doing on active matter mostly, and I have to mention that all my work on active matter is in collaboration with the group in Bari, led by Beppe Gonella here, and the group in Barcelona, led by my former PhD student, Demian Levis, with whom we worked on frustrated magnets actually for his thesis, but now he's, well, after postdocs and so on, he's also interested in active matter, so we're working together again. Okay, so I'm going to change a little bit the order in which I want to do the presentation, because I only have half an hour. So this was a long introduction about melting, but since the focus is on to the definition of active matter, and then eventually go back to melting. I have lots of things here. I don't know if I can go faster, but I don't know how to do it. Oh, too many. Okay, active matter. So active matter is a large system composed of a large number of what we call active agents. So agents could be particles, could be polymers, could be birds, could be fish, each of which consumes energy from the environment, and it uses to exert mechanical forces and then, for example, move, displace, push other things, and so on and so forth. So due to the energy consumption, these systems are intrinsically out of equilibrium. So they are getting energy continuously from the environment. Part of it, they are using it to do work, like move and so on. Part of it, they are giving it back via dissipation to the environment itself. Differently from usual condensed matter systems or soft condensed matter situations in which, for example, when you do shear on a liquid, you are injecting energy as well, but you're doing it from the borders. Here is the agents themselves, each of them, even in the bulk, which are getting this energy. So it's kind of uniform energy injection that you have. And, well, as I said, they're also coupled to a bath in the usual sense of being able to dissipate part of the injected energy into the bath. So this is like a general setting of the active matter systems. And they exist in nature in a wide range of scales, going from the microscopic to the macroscopic. So examples are, as I said, bird, fish, cells, bacteria, going to the large from the small in this line. There are also many artificial realizations. I will show you some. They can be found and made to function in 3 dimensions, 2 dimensions, 1 dimensions. And there's very different ways of attacking these problems theoretically. There are coarse-grained models, like writing field theories that go beyond the Ginzburg-Landau time-dependent ones, and that include terms in those field theories which break Ditten balance. And with this breaking of Ditten balance, you mimic the energy injection and the coupling to the motors, or to the mimic the activation in these problems. Or one can write microscopic models and then do molecular dynamics on those microscopic models to follow the evolution of the particles or the agents one by one, and then try to see collective behavior in these systems. You can do this microscopic modeling in a very detailed way and do some kind of ab initio sort of simulations, or you can simplify a little bit the models and try to pick the essential features of these systems and do some kind of Langemann dynamic sort of modelization of this coupling of this system of interest to the bath, and do some mesoscopic description of what's going on. And this is what I'm going to discuss here. And then there are many, a lot of studies of cellular automata sort of models, a la Abhishek. I will not talk about them, but okay, just to mention that there's also huge literature around them. So these are some examples. So these are the typical pictures of the birds flying in Rome and making these nice structures in 3 dimensions in the sky. But you know, if you go lower in scales, you have these Janus particles. So Janus particles are colloidal particles, which are coated in different ways on the 2 sides of the spheres. And one of these sides is reacting chemically with the environment, with the fluid with which they are put in contact. And this reaction, these chemical reactions, make them displace in one special direction of one side of the sphere towards the other side of the sphere. So it's like having a force applying on a particular direction, along the sphere. But then, of course, since these particles are in interaction with the bath, which is making some thermal agitation on the Janus particles, and on top of that, they interact between them in some way, possibly repulsive way, then they just not make straight lines. They tend to go in a straight line trajectories because of this force, but then the interactions and the noise make them turn. So then they also do some kind of random motion, but of a different kind of just normal random walks, random motion. They do what is usually called either a persistent random walk, because there is a preferred direction over which they want to go over relatively long lengths of time, periods of time, but then they turn, they go in the other direction, then they turn, and so on and so forth. So there is a persistent random motion sort of displacements of the individual particles here. And then, okay, depending on the conditions that you use in your experiment or in your simulation, you can control the persistence time of this random walk. So it's a parameter in your modeling or a parameter in the experimental realization. And then there are other realizations, which are like these ones by Olivier Dauchot in Paris. So he has these granular particles, which are slightly asymmetric because they have 2 feet on which they are posed on a substrate. And these feet are slightly different. So you see there is a point on each of these granular particles here. And this tells you where is the special feet, let's say, and the special foot. And because of this asymmetry, they tend, when he vibrates the substrate, they tend to move in one direction, but then they collide with the other ones, and then you have some collective effects arising because of both the activity, the special direction in which these particles are pushed because of their asymmetry, and the interaction with the other ones because they cannot just jump over the other ones, or they cannot deform either. So there are artificial and natural systems of active matter kind.
Sorry, just a brief question.
Yes.
Could you tell me how big these particles are that are on the vibrating plate?
Oh, they are big. They are like maybe probably the scale on the slide is an actual one. They are I don't know, this size, something like this. So
okay,
yeah,
so they
have big tables. So, yeah, centimeter size. Yes. So they have a big table in which they put all these granules, and they vibrate this table. And the problem with these kind of realizations is that the boundaries have a very large effect on what the systems do. So they have, the what's going on around the boundary is they have boundary effects which project, deeply into the system. So they have to work with strange boundaries not to influence so much the behavior of the granules. Okay, this is a full knowledge developed over the years by Olivier and his work. Yeah.
Great, thank you.
Welcome. So I said that there's Langevin-like equations that are used to model these systems. So one of the standard ones is what is called overlap Brownian particle systems. And so the idea is that, well, you write down a Langevin equation. So I keep inertia, but then you can drop it if you want to go to the overdamped limit. You have some dissipation, friction here, modeled in the simple way, so gamma velocity. Then you have an active force term, which acts along the direction on the particle, special direction on the particle. So this vector n is telling you which is a special direction, but this special direction turns, as I said, and you will see it later. And F act is the strength of the active force. This term here is just some potential term, potential force, which is derived from some potential of interaction between the particles, and you have freedom to choose this potential of interaction. Typically for these problems, the relevant kind of potentials are repulsive and relative, very hard potentials. So you see in the granules, this is quite obvious because they cannot, one penetrate the other one. So it's like hard walls, that, the way in which one interacts with the other ones, and very short range because you don't have other kinds of potentials. But okay, in other cases, you can work with these Mie sort of potentials, which are modifications of Lennard-Jones potentials that make them very, very hard, and only keeping the repulsive part of the potential, no attractions at long distances. And then you have translational noise, white noise, which is related to this gamma R dot via the usual fluctuation dissipation relations for the bath. Okay, so this is equilibrium noise related to the dissipation, but this is the energy injection term that you have in the equations of motion. But then, as I said, the angular direction of the particles is also changing, and this usually in these models you modelize by just noise. Okay, so overdamped motion with some other noise, rotational noise, eta, which is delta correlated like this. So you have a diffusion coefficient, or better said, you have a strength of this angular noise, which is another parameter in the problem. Independent of temperature or related to temperature, but with some independent parameter within this d theta. Here, for certain cases, you can argue that it has to be given by the temperature over friction coefficient and over the diameter of these particles. So this is one way of modeling it, but you can also take it independent. And this parameter here is basically the inverse. You can show that it's the inverse of the persistence time, and it's related to the inverse of the persistence time, and it gives you an idea of how long are these trajectories in straight direction before they turn around. There are two basically independent control parameters that people like to keep in these problems. One is the density, global density, how many particles you put in your volume, and the Peclet parameter, Peclet number, which is, if you look at it, is basically the ratio between two energies. So the numerator is the work that the active force is doing when you translate your particle by a distance which is equal to its diameter. And the denominator is the thermal agitation that the bath is providing to the system. So this is an adimensional parameter, and it basically tells you how strong the activation is. You, of course, could keep...
Leticia, question. So how relevant is the temperature for this kind of systems, actually?
Indeed. So temperature is not that relevant for these kind of systems when you want, I mean, at least the region of parameters we're using it, we just fix temperature and we keep it fixed, and we choose it to be, well, some value that it's more or less important. I mean, where interesting features are observed, and we just don't move it anymore. Yeah, so it's not so relevant. Okay, so this is just to give you an idea of what this Mie potential looks like. If you had a hard wall, it's just a hard wall. But if you have Lennard-Jones, you will have this repulsive part here and then an attractive part at longer distances with a minimum value sigma. This would be the Lennard-Jones here, and with n equals to 6. But if you, first of all, do the WCA trick, which is to translate up the Lennard-Jones and kill the part which goes beyond the minimum to the right, then you have the blue curve that only has the repulsive part and it's 0 later on. And moreover, if you take an n, which is much larger than 6, so for example 32, you get something like the red curve here, which is very close to just the Dhar wall, only that it doesn't fall sharply, but it has a little curvature when it touches 0, and it gets to 0 in some smoother way than just the Dhar wall, and this is better for the simulations. So the conclusion of this curve is that we are working with very hard spheres, and choosing this WCA to take n very large, and this is what is called the Mie potential. So this is what comes in here to describe the interactions between the particles that don't want to go on top of each other. Many simulations and studies have been done in 2 dimensions, and 2 dimensions is interesting for several reasons. One reason is that, okay, many of the experiments as well have been done in 2 dimensions because people work, on surfaces, like in the Dosho experiments, but also with the Janus particles and other sort of things. But I mean, from my point of view, 2 dimensions is especially interesting because phase transitions in 2 dimensions are special. This was the context of the first part of my lecture, which I will not have time to cover. But in 2 dimensions, you have, for example, crystals don't exist. I'm not talking about equilibrium now. So crystals, there are no crystals apart from 0 temperature. In 2 dimensions, you have solid phases, but you cannot have long-range translational order in 2 dimensions. This is Pius, Landau in the past. And in 2 dimensions, you can have exotic phases. So phases where you have quasi-long-range order of orientational kind. So from the solid, well, you don't have long-range translational order, but you have long-range orientational order. You go to exotic phases by either increasing temperature or decreasing density, which have short-range translational order, but quasi-long-range orientational order. So these are interesting phases. And then you go to the liquid. So this is a special of 2 dimensions. And moreover, these 2-step kind of phase transitions, which for long have been thought to be of Kosterlitz-Thouless kind, both of them. More recently, the second one, from the exotic to the liquid, has been discussed, and it has been shown with numerical simulations in the passive limit, so no activation, that it's of first order kind. So there is coexistence between exotic and liquid appearing at 0 activity, which is also interesting to study. The role of topological defects, which were the ones which were supposed to drive these transitions, has to be revisited as well. So there are many issues which are special of 2 dimensions, which merit study, and there's no necessity to go to 3 dimensions, which is more difficult to simulate and maybe less interesting from the fundamental point of view. So, okay, I talked about the potential. So this is a sketch of how a passive particle in interaction with other ones via these Mie potentials will move like in just this is a normal sort of random walk trajectory, while if you have activation, you will see something like this. So this is hard, quite large activation. So you will see these long periods where there is no jerky motion, but almost a straight line motion, and then turns, and then okay, going back in a different direction, and so on. So I will go to the chat because showing you some results about the passive limit and weak activity. Okay, there are many questions. So this I answered already. What is the Mie potential rather than hardcore repulsion use? It's because for simulations it's better. So because of this discontinuity of the derivative around where the Dhar wall would be located, that makes the simulation more stable. I'm not an expert on simulation techniques, but this is what my collaborators tell me. So this is why the Mie is used. Is it supported by the experiments? Well, I think so, yes. In certain cases, you can have some small deformation of your particles, so then, the repulsion is not completely hard, and then you can argue that the Mie is more precise for those experiments as well. Well, there's no crystallization in 2D. Is it some sort of Mermin-Wagner theorem? Yes, it is some sort of Mermin-Wagner theorem, indeed. And moreover, Piles in the 30s what he did was to look at a very simple model of what temperature fluctuations would do on a perfect crystal. And so he modeled a crystal by, he modeled the system as a system of beads coupled via springs. And you can solve the dynamic equations for this system of beads coupled with the springs, just solving the Newton dynamics of that problem. And then you could see that you cannot have long-range correlations of the positions. So the displacements of the beads with respect to the perfect lattice positions will diverge, will not reach constants in the long distance limit in 2 dimensions. It will diverge like logarithms of the distance. So then, in the end, the lattice is broken because the fluctuations around the lattice positions increase with distance. So this you can do analytically, and this is, Pius did it, and also Landau independently. So it's, yeah. How can we put activeness in an on lattice spin model? Something like, yes, active easing model. Yes, you can do it. So there is a paper by Julien Taillère and Alex Solon, where they do exactly that for a particular spin model. And what they do is they break little balance in the evolution of the spins that you propose in a way that it's adequate for what they wanted to do. So I suggest you to look at this model. So the 10 minutes that I have, let me tell you something about the phase diagram that you find at 0 Peclet and at small Peclet in these problems. So as I said, this phase diagram here, I didn't write the axis, sorry for that, is Peclet in the horizontal direction and packing fraction or global density in the vertical direction. At 0 Peclet, you are in the passive case, no activation, just particles interacting repulsively. So you have a solid for large densities. In my slides, solid is always orange, exotic is always violet, and coexistence is always gray, and liquid is white. Okay, so on this axis, what you have is that you go from the solid to the exotic. Is tiny here, but it's there. There is a little bit of violet in between the orange and the gray. And then you have coexistence between exotic and liquid in the gray region, and then you have liquid below. So this coexistence is revealing the first order nature of the transition between the exotic and the liquid. You can prove this with different measurements. You can do, for example, pressure density, pressure as a function of density, and see that you have a loop form of your pressure curve that tells you that there has to be a first order phase transition, like in the van der Waals model, no, for particle systems. You have to have a first order phase transition between the two phases in question. You can also do measurements of local density and see that you have 2 peaks in these distributions of local densities, one corresponding to the liquid and one corresponding to the exotic phase. I see which slides I have here, because this I was going to explain at the beginning of my lecture, just dealing with the passive case, but I don't have to go from the beginning, so I'm doing it here. Let's see if I have plots later on to show that. You can also do distributions of local exotic order parameter, which is a measure of the orientational order in your sample, and see that you have 2 peaks in these distributions over this region of parameters. Then you can add activity. And you can see by adding activity is that for small values of the activity, you keep this coexistence region, but then at a higher value of activity, the coexistence region disappears, and the transition between the liquid and the exotic becomes continuous. So here you have continuous phase transition of Corteles-Taules type, it seems. Here you have continuous phase transition of Corteles-Taules kind as well, but here in this region you have first order phase transition between liquid and exotic. And the first two who talked about this very carefully in recent years and prove it for the passive case have been Bernard and Kraut. And then, okay, we extended it to the case of activity in this paper with my colleagues in Barcelona and Bari. So ways to see, where in which phase you are is to look at correlation functions and see how they decay these correlation functions. So you can look at translational correlation functions. These are in these slides here. And you can look at orientational correlation functions by defining another parameter that measures how oriented these particles are and seeing how these correlation functions decay. So, okay, again, I'm jumping over the precise definition of these other parameters and correlation functions, unfortunately, but just believe me that there are ways to define these objects. Let me see the chat. Isn't the two transitions KT and inverse KT, even in passive case? No, they're not KT. So the solid exotic is KT in the passive case, but the exotic liquid is not KT. And there are different ways to see it. So you can see it, well, from the coexistence properties of these two phases. But if you want to go deeper and you want to go and see whether the disclination unbinding mechanism that is supposed to be behind the exotic liquid transition in the usual Halperin-Nelson-Young picture, then you will see that this is not driving the transition. So in the even in the passive case. So I don't have time to show you the data, but yeah.
Wouldn't that depend on the interactions? For example,
yes. Yeah, sorry, I didn't say it. It does depend on the interactions. So for sufficiently hard interactions, this is what's going on. For softer interactions, you go back to the Costa-Lithaules Halperin-Nelson picture. Yes.
So your results are for the hardcore interaction.
For the hard, yes, for the hard. Also the Bernard and Kraut. So they did Kraut with another student, Kapfer. They studied very detailed the effect of the interacting potential, and they showed, this power law decay, how sharp it should be to get the first order scenario instead of the usual Costa-Lithaules one. Yes. Okay, so I have these distributions. So you see, if I go across the transition at very small Peclet, where I have this coexistence regime, what I see is that for packing fractions within the gray region, I have this double peak structure of the distribution. Here is of local density. So local density is simple. You count how many particles there are in a given box around a position, and you have some length for the boxes that you use. And okay, you fix this length, and you look everywhere in the sample, and you see that there are regions which are more dense, regions which are less dense, and you have this double peak structure. And you can do scalings of these peaks and so on, which I'm jumping over them. So this is the sort of double peak structure that you see when you have coexistence. Instead, if you go through these lines here, in the region where you don't have coexistence, at the higher value of a Peclet, you don't see any double peak structure. You just see one peak structure which is moving towards higher densities when you go, above the into the solid phase, or you go towards lower densities where you go to the liquid phase. So it's just a translation of this peak structure with the density that you see, and there's nothing like what you see on the left side. So this is one of the evidences for having this first order phase transition for small Peclets. You can do analysis of topological defects. I will not discuss it here, unfortunately, because it's very, very amusing. This is work I've done again with these people in Bari. Okay, jump over this, so it's very detailed, but let me go to something more specific of the active problems, which is the appearance of, in the limit of a strong activity, another phase, which is called the motility-induced phase separation phenomenon, which was proposed and demonstrated by Mike Cates and Julien Tailleur in the 2012, I think. And this review article that they wrote more recently. where they discuss this phenomenon in a lot of detail. So basically what happens is that when you increase Beclet very much, you go to a region where the system likes to phase separate into a dense droplet and a dilute gas, if it's very low density here. So this is like what happens in a similar to what happens in an equilibrium problem when let me see if I no, okay, it's not here. So this is like what you have in a normal equilibrium problem, where this axis would be temperature and this axis would be concentration, right? So if you go to parameters within this MIPS region, what the system would like to do is to phase separate into a dense droplet with this density and a dilute environment with this other density. And for example, these are simulations of our group, but there are many other simulations, where you see this dense droplet immersed in these surroundings of gas. So the particles are colored differently according to their orientation, because they have this particular orientation along which the forces are acting. And basically what's going on is that the particles on the boundary are on the right, pointing along the left direction. So they're pushing inwards on the droplet. The particles on the right are pushing on the right direction, so pushing like that. The ones on the bottom up. The droplet together in this way. So the new particles, tend to aggregate onto the droplet, and the ideal concentration of the droplet is given by this density here, and the one of the gas is given by this other density here for parameters within the MIP space. Something other which is also special of these phase separation phenomenon now out of equilibrium is that you have these gas bubbles within the droplet. So there is, you see these holes are gas bubbles, and you can say things about the distribution of the sizes of these bubbles and so on and so forth. Okay, so I'm a little bit late. So let's see what else I can tell you. Okay, this was the comparison, which I said in words, between this motility-induced phase separation and this normal equilibrium phase separation discussed by Kate Santayera in the original paper. Now, something else which can be said about this special droplet is that it's not uniform or it's not homogeneous within the droplet. And apart from the bubbles that I have already discussed, there's also patches of different colors that we highlighted here. And what are these coloring meaning? The coloring is meaning that there is different orientational order within this dense droplet. So within the dense droplet, there is patches which are actually of microscopic length, not macroscopic length. So the length of the droplet is macroscopic, is similar to the system size. But within the droplet, you have microscopic patches of different orientation, different exotic order, local exotic order. And there are topological defects on the interfaces between these exotic patches, which are also interesting to study. So, okay, I'll go over these. I don't want to make it too long, but okay, this is the kind of zoom over one region within the droplet, and you see these different orientationally ordered regions with topological defects, which are highlighted here in red and blue. And what are the topological defects in this context? There are particles which don't have 6 neighbors around them, but they have 5, 7, less or more, but less or more are very rare. So they have 5 or 7 neighbors around, and they break this hexagonal perfect ordering at 0 temperature and no activity that the system would like to have. And these are located mostly along the interfaces between these exotic patches, and this is also something interesting that can be studied. Okay, I'll jump over this. So, okay, there's a lot of things that could have been said. So in the passive case, you have this solid exotic a la BKT transition that when you include activity remains BKT-like. I didn't have time to discuss it, but the exponent characterizing these BKT divergences that you have on the transition are independent of Peclet. This we seen numerically. I think it can be proven analytically. Well, after the summer, probably the student will start working on this. It should be able to be proven analytically, and there's some kind of universality along this solid exotic phase transition for any Peclet. Then there is the exotic liquid transition with this peculiar one-first order kind at low Peclets that stands for a weak Peclets and then becomes BKT again, and then matches the MIPS for even higher Peclets, which is also interesting. Then there are percolation features about topological defects, clusters of topological defects, which I didn't have time to discuss, but they are also interesting, I think. And then there is this motility-induced phase separation at high Peclets. You can say many things about how these stationary states I talked about, which are non-equilibrium stationary states because of the energy injection, but how is it reached, this stationary state? So you can do coarsening, you can do analysis of approach to asymptotic non-equilibrium states. In this case, study the growth of the dense bubble. Okay, lots of things could be said. I'm not going to do it, unfortunately. So now I think it's time to finish. So I will stop here. I will thank you for the invitation. I hope I can do it in presence next time as soon as it's possible. And okay, I'm ready to answer some questions on whatever subject you like from the students or the permanent people. Thank you.
Thanks. I think there's a few chat questions.
Yeah, let me go to the chat. Can any of these active matter phases that you described be observed in nature? Oh, yes, yes, yes. So I didn't show experiments, but in experiments you can see clustering of the active particles, and this motility-induced phase separation it has been observed in experiments as well. So yeah. And people in experiments are starting to look at this orientational order as well. This especially the group of Denis Bartolo in Lyon is doing this right now. And you know, so these things can be studied rather well experimentally. So yeah.
And what about, are there any physical systems where these phases are observed? Because in the beginning you talked about, you know, flocks of birds and school of fish, but yeah. I don't think that these in these systems you would expect, you know, a motility-induced phase separation, for instance.
Well, but they cluster, you know, so it's not exactly the same, but they go together, the fish and the cardamons and the flocks of birds, so they do cluster. So this is similar to the motility-induced phase separation, although it's not exactly the same. But in these two dimensions I was talking about, with the colloidal artificial systems of active matter, or with the bacteria, you can see this clustering as well. So bacteria is a little bit different because they are elongated objects, and actually being elongated, there are differences which appear in the phase diagrams that we and other people have studied as well. So it's not exactly the same, but there is clustering as well, and there is phase separation. Yeah.
And maybe just one more question: is it known what the influence of hydrodynamic interaction is on these phases?
Yeah, so we don't include them, but there are other people who are including in the hydrodynamic interactions, and but the ones who do include hydrodynamic interactions, often they work in the low density limit. But I think that high densities and high Peclets, I'm not so sure it has been studied with hydrodynamic interactions, but they are important in certain cases, of course, yes.
Thank you.
Yeah.
Hello, ma'am.
Hello?
As there is this phase transitions are very interesting. There are very interesting phase transitions. So, can you give some recipe? How can we identify it analytically, like in terms of free energy? How can we write free energy for this system?
Oh no. Okay, so these systems are essentially out of equilibrium because they break the balance, and there is this energy injection due to the activity. So in principle, you have no right to write free energy. There is no free energy. But what you can do, and some people are doing this, is to write these generating functionals with the Martin-Cicharot's sort of formulations, and from them you can write what they sometimes called large deviation functions. And then, in the exponential of these, like Ginsburg-Landau, in the exponential of these large deviation functions, you will have functions of the fields, the coarse-grained fields that represent the problem. And these play the role of free energies, but they're not really free energies because you are out of equilibrium. So, yeah, so this is what you can try to do.
Thank you.
Yeah.
Okay, so
Yeah, I have one question. Yeah, so Leticia, so you said before in the high Peclet number, these hexatic and solid liquid transition, it again becomes KT for your problem. Is that?
Yes.
So when you so when you see that, is there some, when you look at it, is there some signature that you measure, which where you be able to say that it becomes KT, like 1/4 kind of things? Or,
yes, exactly. So it's very difficult, to be sure. Huh? So one has to be a little bit careful there. But the correlations seem to follow these exponents of the KT at the critical point, on the critical line. But I have to deal with the correlations of this kind. What do I have? So you have to deal with this kind of numerical data. So, you have to be careful about the conclusions, right? So the 1/4 is somewhere here, and the other one predicted is somewhere there. So, okay, this is one of the possibilities of, how you can claim that you have these first order phase transitions, Kosterlitz-Thouless phase transitions. And the other thing is that you can look at the defects. So you can look at what happens with the disclinations and how they separate when you go across the transition for the different Peclets. So this number here, these Peclets, are all in the region where you have already left the coexistence. So these are supposed to be corresponding to Peclets where you have Kosterlitz-Thouless kind of transition, and then you can try to see how the density of disclinations, of free disclinations, depend on the control parameter close to the transition, and you can try to see whether you have the exponential, going down to 0 predicted by Kosterlitz-Thouless with the nu equals to 1/2. Okay, and then again, it's very, very difficult to be sure about what you're saying. But if you try to do honest fits, well, 1/2 is not bad. But okay,
so you could visually see that the bound states of disclination or dislocations are forming and bound transitions is happening.
Yes. But everything is, for the disclinations, everything is much more complicated than from the dislocations. For the dislocations, you can do the fits, and they are rather sure, these fits. For the disclinations, everything is a little bit more dirty. And moreover, on this phase transition, you also have clusters of defects. You don't have only, isolated disclinations. There are no isolated disclinations. They are always very close to clusters, and the clusters are very big. And then, everything is accompanied by all these clusters. So everything is, again, much more complicated. So I wouldn't, be so sure about what's going on, even for large Peclets between the hexatic and the liquid transition. And actually, this is, I think I have it here. You see this curve here, what is telling you, these red curves here, is telling you which is the line on which these clusters of defects percolate. This is we studied as well. So you have a critical percolation, actually, phenomenon arising within the liquid. So, in all this region, you have clusters of percolate, of topological defects which percolate, added to the isolated disclinations that appear below the line which separates the violet from the white. So it's a very complex situation. Yeah. While here, everything is much more clear. So here you really see the dislocations that, the four groups of 4 of topological defects that separates in groups of 2, and these groups of 2 go far away, and you can claim that they are isolated.
And do you think that there would be similar Coulomb gas kind of pictures in these? Like, is that the hope that you would be?
I think so, because everything works so fine on this line, at least on this line. I can show you the behavior for the dislocations. So you see the dislocations are so clean. This is the density of dislocations, and the lines are the fits, well, done in different ways, but don't care so much about the different ways. These are the fits to the Kosterlitz-Thouless kind of divergence. So you see that they work super well, especially at low values of Peclet. Then at high values of Peclet, okay, the density of these locations becomes lower and it's difficult to tell. But here it's working really well, no? Close to this critical transition, which is signaled by this vertical black line here. So so I think that for the dislocation, for the solid exotic transition, there is universality, and the Peclet doesn't play a role. I would like to show it, I would like to write the RG equations, well, and see whether we can deal with them and see whether the universality arises. So it's something that we would like to do with the student in Bari and with Fred van Bischelen again in Paris.
And the last question is, so how universal are these phase diagrams? I mean, if you choose, let's say, active on-stream Ledbeck process or others, would you see a very similar universal phase diagram behavior?
I don't know. Yeah, I mean, I think that the more detailed phase diagram, at least on these parameters, is the one that we looked at. I can tell you that if you change the shape of the particles, the phase diagram changes. I think I have it. If I can go somehow quickly, I don't know how to go more quickly. Yeah, okay, maybe like this. So I may have it by the end. Oh. No, I don't have it. I'm sorry for that. So what happens basically for the dumbbells, which is like elongated particles made of two beads joined together by a spring. Here it is. So you see, this is the comparison between, these are the active Brownian particles, these are active dumbbells. And dumbbells are just two beads joined together either by a spring or by a line which is not able to fluctuate and not to bend. So actually we're working in this limit in which the two bits are stick together and they don't bend nor open up. And in that case, what you see is that the MIPS phase at very high Peclet goes down all the way to 0 Peclet. So there is no, this part, this breaking of the MIPS and the phase separation at 0 Peclet, phase coexistence, sorry, 0 Peclet is not interrupted. And okay, we can understand now after many years why the beats, the dumbbells behave differently from the discs. But so then, there is even the form of the particles which have an effect. So I think that there is a lot of non-universality in this sense.
Okay.
Yeah.
I think there's a question from Lehan. Hi, Lehan.
Hi, Lehan.
Oh, hi, Leticia.
Hello, how are you doing?
Yeah, that's most of your lecture, but it's really interesting. So I have a question about the dynamics of these disinclinations. So in a equilibrium system, you can try to make them to move by probably applying a shear, right? And also in a superconductor field, with a magnetic field or something, you can drive the vortices. So here, have people done something similar and study kind of a transport?
No. I think that the only, really, well, there were some studies by Marjolijn Dijkstra on the defects, together with a Chinese collaborator of hers. But there's very little done on these defects in the context of these particle systems. So we have done, a lot of analysis of the number densities of these dislocations, but we haven't made them move, as you say. It's something we have in mind to do in the future, but we haven't done it. Yeah.
Okay, thank you.
Yeah. Yes, but yeah, for sure. I mean, the surprising.
Nice to compare.
It would be nice to do it, yes, because something which is surprised us is that there are no free declinations in the end. I mean, the declinations are always so close to other defects and they don't move around. They even in the passive case, they are kind of stick to the vicinity of other defects. And so this goes beyond the usual, it goes beyond the usual picture. Yeah.
Thank you.
Yeah, thank you, Leihan.
Okay, so so maybe we stop here. So I would like to request everyone to maybe unmute yourself or use your reaction buttons to really thank Leticia for this really amazing lectures. So please unmute yourself and thank.
Thank you very much.
Okay, thank you very much. Thank you very much. It was.
And Leticia, we hope to have you at Bangalore and ICTS sometime soon.
Yes, let's hope so. Let's hope that, I was talking about StatFis with the colleagues here in Cargés, and we were all willing to be able to go to Asia next summer. So let's hope that the situation calms down and we can all go and visit you all around. Yeah. Okay.
Okay, thanks again.
Okay,
bye.
thanks. Yeah.
Thank you very much. Thank you all.
Thank you.
Thank you so much.